Dear student, as I had said in my last lecture, today we will be discussing the helical motion of charged particle under moving under a magnetic field. So how is that possible? Let's discuss it over here. Supposing we have a magnetic field, uniform magnetic field like this, in the lying along the horizontal direction, and across it, if we project a charged particle, let's say plus qm, that is whose mass is m and charge is plus q, if it is projected like this with the initial velocity at an angle to the b vector. Now if the v vector's component is taken, this is v perpendicular and this is v parallel. Now supposing if this is theta, then v perpendicular is equal to v cos theta and v parallel is equal to v sin theta. So we have these two components of velocity. As we had seen earlier, that if the velocity is parallel to the b vector, then the force due to the magnetic field is zero over here. Why? Because the force is given by the relationship qv cross b. And if v is parallel to b vector, then theta between them is equal to 0, and if it is anti-parallel, it is equal to 180 degrees. So in both these situations, we have q, v, b sine of theta. Okay, since theta is 0 in case of parallel and 180 in case of anti-parallel, so in both the case, f is equal to 0. If theta is equal to 0, then sine 0 is 0, we have f is equal to 0. So no force results if a charged particle is projected parallel to the magnetic field. So this component, that is v parallel, won't be producing any magnetic field, force on the charged particle due to the magnetic field. Rather, this v perpendicular is the component of the velocity which is responsible for the force which is resulting out of its motion in a magnetic field. So v perpendicular is equal to v cos theta. Now let's analyze and see the direction of the motion of a charged particle in a magnetic field. So from the cross product, the direction would be v cross b, right? So this is v and this is b. Okay, so first vector to second vector. So the force vector will be lying somewhere into the plane of the whiteboard. So if the force is inwards, the center of the circle which it will execute also lies inside into the plane of the board, and therefore what results out of it is a circular motion like this. Okay, so the circular motion produced will be like this. Okay, so this will be a circle going into the plane of the board. Okay, so this will be executing this circular motion, and since the particle is also having a velocity parallel to the b vector, therefore it will pull the particle along the b vector. So this will stretch it while rotating. So the resulting motion would be like this, a helical path like that of a spring. Okay, the circular motion is resulting out of the perpendicular velocity, and the axial motion is resulting out of the velocity component parallel to the magnetic field. Now let us describe one important parameter which is known as the pitch of the helix. So what is pitch? Pitch, as you might have studied in your high school, pitch is the distance moved along the axis during one revolution. So when it completes one circle, what is the axial distance that it moves? This is known as the pitch. Let's say that this is equal to d. Fine. So what will be the pitch in this case? Let's first of all find out the time period. Okay. So time period, as you know, t is given by 2 pi m divided by qb, as we had seen from our previous discussion of the spiral motion. T is equal to 2 pi m by qb. Now, what we have over here is this is independent of the velocity. Okay. So during one time period, the distance that it will move through is equal to v parallel into t. So the d value will be equal to v parallel is v sine theta into t is what? 2 pi m divided by qb. So this will be the pitch of the helical motion resulting out of situation given over here. Okay. So as we have seen that where it is used, if a spray of particles, okay, if the subatomic particles, they cannot be projected one at a time, therefore what we have is spray. Okay. Okay. So this type of particle is sprayed onto this magnetic field. What has happened is they given all the remaining things as the same, that is mass of the particle, since they are of the same nature, that is, let's say if a beam of protons is shot through this magnetic field, then what will happen is that since they have the same mass charge and the magnetic field is also the same, therefore the time period will be the same. Therefore after one after one revolution, they will all be at the same position. Okay. So let's say over here, some of them are like this. So the time period will be the same, therefore they will be meeting somewhere over here. So we have this sort of things, okay, used in some practical situations. Now this particular what do you call aspect is also used for separating the charged particles. Okay, for the separation of the charged particles, we also have this sort of thing. Supposing if we have isotopes, okay, now isotopes are what? They are the different atoms of the same element having same atomic number, that is atomic number is same. Okay, atomic number is same, but atomic mass is different. So these are known as the isotopes. For example, U-235 and U-238. So they are the isotopes of the uranium, that is the element is known as uranium. Now in the scale of the laboratory, if we want to separate these two, okay, since they are the atoms of the same element, therefore chemically they are not different, so any chemical method to separate them is useless. Therefore we use the above technique to separate the charged uranium atoms, okay, if the uranium atoms are charged and if they are shot through a magnetic field, let's say supposing this is the magnetic field, and if the charged uranium atoms are being projected like this in the magnetic field, then what has happened? We have seen that R is equal to mv by qb. Okay, so if the mass is different, then the radius is also different. So as we have seen that U-238 is having a greater mass, uranium isotope of uranium having 238 mass number is more heavier as compared to U-235. So these two get separated over here. How? Because the radius of a massive particle would also be more, and therefore the 238 will be having a greater radius, okay, and U-235 will be having a smaller radius. So when it comes out of the magnetic field, so this is supposing the boundary of the magnetic field. If we have a separator over here, okay, so the lower one will be having U-235 and the upper one will be having 238 because the radius is R2, and if this is R1, R1 is, that is R238, radius of 238 will be greater as compared to 235. In this way, at a laboratory scale, at a much lower scale, where we don't need to separate such large amounts, we use this particular technique in order to separate the uranium ions. Okay, so it is not only used to, what do you call, study, is not used for the study of the smashing of the particles, it is also used for separating. So several other uses of this particular technique is employed in various practical situations. So students, today I end my lecture over here. Next, in my next lecture, we will be discussing magnetic force on a current carrying element, and then we will continue and discuss the torque on a current carrying loop. Okay, metallic loop, let's say, or a loop of conductor. Okay, so we will be studying these two, and from our last discussion we will see that how the rotatory motion of the fans that we have, or anything, if we wish to rotate it, okay, we can employ this particular principle. Okay, so herein I end my lecture. Hope you to see you in the next lecture. If you have any suggestions, please comment. Thank you.